Okay. All right. So where was I? So we have been discussing the right inverse and left inverse. So the inverse matrix. Well, technically speaking, so inverse matrix only exists only for the square matrix. But even if your matrix is not square, but then you may not be able to. Then you cannot get a inverse matrix. You may have a right inverse or left inverse. So I think I have proved the number one. So if this guy has a solution for all such b's, then you have a right inverse, which is this. And in that case, m is less than equals to n. So in other words, A must be a wide matrix, right? Okay. All right. And today I will prove the number two. This time, if you have at most one solution, so you cannot have two different solutions for the same B. In that case, you have the left inverse, the B. And in this case, m must be greater than equals to n. So in that case, A must be a narrow matrix. Okay. All right. Okay. So the proof number two. I'm going to claim that this statement I'm going to show you that this statement is equivalent to columns of A are linearly independent. Which side is easier? I guess both directions are easy. So I will prove the if part first. Well, suppose that the columns of A are linearly independent. Columns of A are linearly independent. And now, also assume that we have two solutions for same B. The one solution, I'm going to say X, and the other one, Y. Sorry, I changed my mind. I'm sorry about this. If AX is B and AY equals B, then AX minus Y must be the zero vector. Okay, because if you subtract both sides of these equations, then you get this. And considering the matrix A as a collection of n column vectors. So this is A, and this X minus Y, for simplicity, I will just say this is A. X1, Y1, X2 minus Y2. I'm going to write in component. So from X1 all the way to the Xn minus Yn, and this guy equals to 0. So this equation is this. And well, as always, this is X1 minus Y1 times column vector A1, An and equals to 0. Okay. Oh, okay. So I'm done. So since we are assuming that columns of A are linearly independent, and therefore the only possible solution for this vector equation must be the trivial one. Okay. So xi must be the same as yi for all I. Therefore, x and y must be the same vector. Okay. All right. Okay. The other way, other direction. Now, this is the only part of the statement. So, okay. So now I have to assume that ax equals to b. So let us suppose this system of equation has at most one solution for all possible b's. Then now I have to show that columns of A must be linearly independent. Okay. How do I prove this? Well, maybe I will try to prove by contradiction. So assume that columns of A are not linearly independent. So in other words, they are linearly dependent. Dependent. Okay, so if columns of A are linearly dependent, then that means the null space of A must be non-trivial. Okay, so that means I must be able to find at least one non-zero vector from the null space of this matrix. So there is a non-zero vector xn in the null space of A. Then, this is easy. Then if X is a solution of AX equals to B, then X plus Xn is a solution too, right? Okay, because the Xn was chosen from the null space of A, so which is clearly contradiction. Okay. All right. So this condition is equivalent to the columns of A are linearly independent. Therefore, the null space of this matrix must be 0. Okay. So null space of A must be the trivial subspace, which has the 0 vector only. Then and also we have to make sure. So we have to remember the dimension of the null space of A is the what was that? The number of columns of A minus rank of matrix A. So this one must be. So I said this is n by n matrix. So this guy dimension of this guy must be n minus rank of A, right? And because of this guy has the 0-dimensional vector space. So which implies the rank of A must be n. And this implies, and rank of A is the same as rank of A transpose. So this is also n. Therefore, C, the row space in other words, column space of A transpose must be Rn, right? Okay. All right. So A T so that means this guy was n by n. Now so A transpose is n by n, right? Therefore, and the column space of A transpose, well, was the whole entire Euclidean space Rn. Therefore, for any choice of B, so you can find at least one solution. Okay. At least one solution for all B in Rn. That means, now I can make use of the statement number one. So in this case, so if this guy has a solution for all such B's, then A has a right inverse. Okay. Then A transpose has a right inverse. Say I'm gonna say this is B transpose. And hey, what was the dimension of this? So this is n by n matrix. So in this case, n, which one is greater? This time, yeah, n is greater. Okay, I'm sorry. So if this is, well, sorry, I just confused. It is m by n, and in this case, m is less than equals to n. Now this is n by m, so yeah, n is less than equals to n. Okay, all right, okay. So there is BT such that this is the right inverse. So A transpose B transpose is the identity, and so in other words, there is a matrix B such that BA is identity and M is greater than N. Okay, so we are done. Okay, great. All right, so this is the end of the proof. All right, so what do you know from this theorem? So what do you know from this statement number 1 and 2? Okay, so let us just forget about the proof of this. And so if you understand the theorem, and it clearly says that in order to have a left or right inverse, then, well, the number of possible, the maximum possible number of linearly independent columns of A. Yeah, sorry, I'm sorry. I messed up. You must have, in order to have left or right inverse, you must have the maximum possible number of linearly independent columns that the dimension of A allows. Well, so suppose that you have a matrix A, and if you have a matrix A wide matrix, then the number of rows is less than number of columns, right? And in that case, if you want to have a left or right, if you want to have a right inverse, then the number of linearly independent columns must be the same as number of rows. Then in that case, there is a right inverse. So always the wide matrix times followed by the narrow matrix is going to be the identity matrix. So this is, and on the other hand, if you want to have the left inverse, then your matrix must be a narrow matrix, okay? And the number of linearly independent column must be the number of column, right? So you also you must have the maximum possible number of linearly independent columns. In that case, then you have a left inverse. But this time around, the same thing is true. So in that case, your matrix A must be the narrow matrix, and your left inverse must be some another wide matrix. And left times wide times narrow is going to be the identity. Okay. I just keep saying that you must have, so there's one slogan, so you must have the maximum possible number of linearly independent columns. Such a notion is very widely used, so we actually gave it a name. I have an m by n matrix. If in this case the maximum possible number of linearly dependent columns, or in other words, it's a maximum possible number of linearly independent column is the minimum of n and n, m and n, m and n. Sorry. So this is your maximum possible number of linearly independent columns, and if the rank of A happens to be the same as the maximum possible number of linearly independent columns, then we say A is a full rank matrix. The full rank means that full rank means you have the maximum possible number of linearly independent columns. So if your matrix is full rank matrix, then then you have left or right inverse, depending on the dimension of your matrix. Or if any full rank matrix happens to be a square matrix, then you have like both sided inverse. Okay. So much for the theory. Now, let me turn to an example. I have a wide matrix. So then this is 2 by 3 matrix. And as you can see from this picture, this is actually full rank matrix. So I have 2 linearly independent columns. So in that case, this is a wide matrix. So I should be able to find a right inverse of the matrix. Okay, so let me try to find one. To find a wide matrix, then I will need to solve 2 systems of equations. X1, X2, X3. X3 is 1 and 0. And I have to find the solution of the system first. And also I have to find the solution of this system. And what is this? I have 2 equations and 3 variables, 3 unknowns. So the solution may not be unique, but it just suffices to find just one single solution. For x1 is 1 and 5x2 equals to 0, and there is no such condition for x3. So x3 can be just anything. So x1 is 1/4 and x2 equal to 0, and x3 is just can be anything, just free variable. And for this equation, for system of this equation, x1 must be 0 and x2 must be 1/5, and x3 can be anything. So, therefore, the right inverse of this matrix is 1/4, 0, and just any number. I'll just say u. And the second column is 0, 1/5, and v. So this is the right. So this is the right inverse of that matrix. So as you can see, so right inverse is not unique. All right. And I was able to find very interesting remark from our textbook. Well, suppose that m is greater than or equals to n. So in that case, A is the narrow matrix. Then and so I have this is narrow matrix, and also assume that A transpose times A is a invertible matrix. In this, under this assumption, then this guy, so A transpose A and inverse of this is a square matrix, right? So this is a n by n matrix, and you take the inverse of this n by n matrix and multiply by A transpose, and it says this is a left inverse of A. Why is that? Because, well, if you multiply this guy by A, so you put A on the right, then then everything is so simply A transpose A inverse minus times A transpose A. So it's going to be identity, right? Okay, and for because of the same reasoning, if A is what wide matrix, then and if this guy is invertible, then this is going to be the right inverse of A. Okay, so this is very useful to know. But however, there is one question that comes in my mind. So these two formulas are true if these two matrices are invertible matrices. But when those two matrices are invertible, so our textbook doesn't say anything about the condition. And actually, I may be able to tell you the answer of the question by the end of the semester. So let us okay, let us not worry about this for now. And another proposition. Now, let me try to be another extreme. So we talked about the full rank matrix, and on the other hand, the matrix with the least possible number of rank is the zero matrix. So the zero matrix has the rank 0. So that is the only matrix that has the rank equals to 0. Okay, but I am not that much interested in the zero matrix because everything equals to 0. And the other one is, what if your matrix has rank 1? Rank 1 means that your matrix has only one linearly independent columns, right? So that means except for the non-zero one, then all the other guys is nothing but the scalar multiple of the first one, right? Then in that case, if your matrix has rank 1, then you can actually factorize the matrix into multiple of row vector times a column vector. I have an m by n matrix. has rank 1. Then there is a n by 1 column vector, which I will name A, and 1 by n row vector B. Sorry. I just changed my mind. A 1 by another column, n by 1 column B, such that A is A times B transpose. Okay, so let me check the dimension first. So this is n by 1. This is n by 1. So if I take transpose of this, then transpose of the A B transpose is going to be a row vector, which is 1 by n. So multiplying these two, I will get n by n matrix. So dimension-wise, this is correct. So how do I know such two columns A and B exist? Because A, matrix A being a rank 1 matrix, that means every other column of A is nothing but the scalar multiple of the first one. C n minus 1, A n A1. So everything is just a multiple of A1. Therefore, this can be written as A times 1 C1 C2 although C2 is invisible. So this matrix can be written as this column times this row. Okay, and I'll just say this is my B transpose. Then proof is claimed. Then the claim has been proved. Okay. All right. Okay. Now we are in section 2.6 about the linear transformation. Okay, so why do we study matrix? Okay, let me just go back to the very beginning. So why do we study matrix? Well, we study matrix for now, as of now. So I feel like we study matrix in order to solve the system of linear equations. Okay, so it looks like we only need a matrix for the linear equations, but well, that is actually not quite true. So well, matrix is very useful. Matrix is very useful when you especially try to describe some sort of functions between two vector spaces. Then what do you have? So what kind of function do you have between any two vector spaces? Well, you can just say, you can just try to declare any random functions between two vector spaces. But well, in the world of linear algebra, there is one very special type of functions that we really care about, which is a linear transformation. So linear transformation is nothing but a function between two vector spaces which satisfies very special criteria. So which I will introduce right now. I have two vector spaces. And I want to consider a function between them. And we say this function is a linear transformation, or shortly, just we say linear. Linear transformation from vector space B to vector space W if the function satisfies this condition. For all scalar A, B, and all vectors so this is our definition. So definition is very simple. So well, shortly speaking, so in order to be a linear transformation, then function must the function must respect the notion of the scalar multiplication and the vector addition. So well, in order to be linear transformation, well, addition of two vectors transformed is the same as transformed and added. And same thing is true for the scalar multiplication. So this is a linear transformation. And in our textbooks, so they came up with very interesting examples of the linear transformations. The rotation. So rotation can be considered, well, rotation is a linear transformation. So why is it? I want to define a function, which function, namely t theta, from two-dimensional Euclidean space to two-dimensional Euclidean space. And how is it defined? Well, if you plug in any vector, any random vector v to this function, then it is going to give you the v rotated by theta radians to the counterclockwise. So this is t theta of v. And I want to claim that this function is a linear transformation. Why? Because, well, suppose that you transformed t theta of v plus w. So suppose that so then that is going to be the same as t theta of v plus t theta of w, right? Okay, so yeah, so this is a linear, and also suppose that you stretch this vector by like factor of 7, then t theta of 7v is going to be the same as t theta of v transform first and multiply by 7. And they are the same thing, right? So clearly, this rotation is a linear transformation. Okay, so, and what now? What about the reflection? Now I want to define a function from R2 to R2, but this time this is TL. What is L? So L is nothing but a random one-dimensional space, subspace in R2. And T of L means nothing but this guy reflected about this axis of L. So those two guys have same magnitude, but well, this is the right angle. Is it linear transformation? Yeah, it has to be. Yeah. So well, TL of V plus W must be the same as TLV plus TLW. And if you TL of alpha times V is going to be TLV times alpha. So they are all the same thing. So this is also linear transformation. Well, I'm not going to spend too much time, but well, the projection, the last one is the projection. So again, this is the map from function from R2 to R2. And projection, well, and this L means another random, another one-dimensional subspace in R2. And P of L means, well, P, this letter P obviously stands for the projection. So if you project this vector onto this one-dimensional subspace, then the resulting vector would be this blue vector from the origin to here. And I'm going to say this is my PL of V. And again, by same reason, this is a linear transformation. They are all linear transformations. And where these are very geometric aspects, these are very geometric examples. And also, I have one very algebraic example of linear transformation. Let P be a space of all real coefficient polynomials. So polynomials on, well, variable x. And this is clearly this is a vector space. Well, because you can add two real coefficient polynomials, and you can also multiply any polynomial by some scalar number. So this is a vector space. And the derivative, well, this is a formal derivative. And the integral is antiderivative, indefinite integral. Those two things are obviously they are linear. So this is also considered as the derivative itself and the indefinite integral. They can be considered as a linear transformation on this space. Okay. All right. Now, I will say all these linear transformations between these vector spaces, they can somehow be related to, they can be associated to a matrix. So every matrix can be represented by, every linear transformation can be represented by some matrix. So this is the point. This is the the most important claim that I'm going to introduce for today's lecture. So every linear transformation between finite dimensional vector spaces can be represented by a matrix. So if you believe in this statement, then, well, matrix is not only useful for solving the linear systems of linear equations, but matrix is also very useful when you try to understand a linear transformation. So let us consider a linear transformation T, so from V to W. By the way, representing a linear transform by a matrix is only possible for a finite dimension between finite dimensional vector spaces. So, well, for instance, the last example, the space of all real polynomials. This is not finite dimensional vector space. So the derivative and antiderivative cannot be represented by the matrix. So I have to also point out this. So this is only true for the finite dimensional vector spaces. Okay. So anyway, I have two vector spaces V and W, and let me say the dimension of V equals to n, and dimension of W is m. Now, how do we represent this guy by a matrix? So in order to do that, then first I will need to introduce a basis of this domain space and the target space. I have chosen any set of bases for these two spaces. W1 W M. Their bases vector spaces and W respectively. Respectively, I mean by, so this is a basis for V and the B2 is a basis for W. So why do we introduce the basis? So introducing basis, the entire point of introducing basis means, so if you have basis, then you can actually pinpoint any vector by collection of coefficient. So then for any vector from V, so then this vector can be written as C1 V1, written as a linear combinations of these basis vectors. So collection of each of these, well, so tuple of these n coefficient can be identified to this vector. So this is why bases are so useful in computation, in practical computation. Now, let me just plug this guy into our linear transformation T. Then, since, well, T of V must be not the member of V, but member of W. So this guy, I must be able to write down this guy as a linear combinations of W1 to Wm, right? So, but before I do that, so let me replace this guy by this linear combination. And also, T was assumed to be linear. So this is T1, C1 times TV1, Cn TVn. Okay. So this is, well, this last equation actually tells us why linear transformation is so easy and important. Well, because, well, suppose that you have any random functions from any two vector spaces. Then in that case, computation of, well, in generally speaking, computation of a function at some certain point is not easy. So it usually requires a bunch of computation, hard and tedious effort. But on the contrary, so if you try to compute not just a random function between two vector space, but if you want to compute a linear transformation, then everything is so easy. So suppose that you can compute each of these guys from TV1 to TVn. So if you can compute these n vectors, the image of these n vector, the image of each of these basis vectors from V, then that means then computation of other point is an automatic consequence. Why? Because if you know each of these values, then you can compute the image of this guy just by multiplication, right? So understand, so this is why linear transformation is so easy. So I mean, so this is my belief, but well, practically speaking, so linear transformation is the only function that we can compute. So if function is not linear, that is almost impossible to compute. So because of this reason, so we try to approximate every function by a linear transformation, and we try to compute them. Because if not linear, otherwise we cannot compute in general. All right. All right. So now we understand computation of this basis vector is very important to understand the linear transformation. And well, again, this guy must be a member of W. So I must be able to write this guy as linear combinations of these basis vectors. I would say this is a 2i W2 a mi w m. All right. So well, even though I have written down just one single equation, but I have n many such equations. Now, the matrix representation of linear transformation T with respect to the basis B1 and B2 is an m by n matrix one, two, a two, two, a m2, a one n, a two n, a m n. So the matrix representation of this guy, this linear transformation, is collection of. So what is this? This is a collection of these numbers, these coefficients. So I mean, so precisely speaking, every column of this matrix is nothing but the array of these numbers. Okay. So this is TV1, TV2, TVN. So I feel like this n by n matrix contains every information on this linear transformation T. Because I told you, to understand this number means, well, you actually find the image of these basis vectors. Therefore, being able to so inclusion of all these numbers. So therefore, this matrix must contain every possible information you want from this linear transformation. So, so why is this so important? And how do we make use of in practical computation? You should be able to see this if we multiply this matrix A by a standard unit vector 1, 0, 0, 0, then this is A11, A21, AM1. So is A1n, A2n, AMN. Okay. So combining all this, so well, I can say if you multiply any random column vector, so any column vector from C1 to Cn, then this is going to be C1 TV1 So, well, this is, well, I told you this is, well, each of these guys, well, not exactly TV1, but this is a, well, precisely, well, technically, so this is precisely speaking, so this is a array of coefficients written in terms of basis vector W1 to Wn, right? So, suppose that you multiply by this guy by this random column vector, then the resulting matrix would be another column vector, right? But each of the but the component of this column vector on your right must represent what? Must represent the resulting vector in terms of written in terms of, well, precisely this resulting column means the coefficient of the resulting vector, well, written in terms of basis W1 to Wn, right? So this is the idea. So once you have matrix representation of your matrix representation of linear transformation T, then if you multiply this guy by some coefficient, this coefficient means that this coefficient was obtained by using this basis, then you're gonna get, what you're gonna get is another column vector, but this column vector contains the coefficient of the resulting vector, which was written in terms of this basis. So, well, you plug in coefficient, then you get another coefficient. But these coefficient, well, then you have to actually translate the result. So your input coefficient was given by basis from V1 to Vn, but the output coefficient was actually given by the basis vector W1 to Wn. And I'm gonna say this is, just to emphasize, this matrix was obtained from linear transformation T and choice of basis vector B1 to B. So the idea is, so if you do not choose the basis vectors, then you cannot get the matrix representation. So to get the matrix representation of any transformation, then first you will need to specify the basis vectors from the domain space and target space. Then you can get the linear matrix representation. Okay. Suppose that I have so I just tried to came up with some random example. I have a linear transformation from R2 to R3 with respect to these bases. For this space, I have chosen these guys as my basis. Well, these are standard basis vectors. And for this space, I have chosen these guys as the basis for the target space. And I just declared my vector, so linear transformation, well, by, well, just declaring the vectors of each of these basis vectors from this domain space suffice to specify the entire linear transformation. So I have just defined T of E1 to be this guy and T of E2 to be that guy. Now, what is the matrix representation of this linear transformation with respect to these bases? That is very easy. Then the matrix representation of this, I'm going to say just standard basis and standard basis. Standard basis to standard basis must be just copying this coefficient and write down in vertical manner. This one must be the matrix representation of this linear transformation. And having this matrix, then you can actually compute the linear transformations of any vector in terms of the linear combinations of bases F1, F2, F3. So, what is T 2 times E1 plus 3 times E3? How do we compute this? Well, you can try to use this guy, so T of E1 is this. So all you can do is to just multiply this guy by 2 and multiply this guy by 3 and add it all together. Yeah, this is something what we can do. But since we have the matrix representation of this transformation using this basis, so instead of doing that, I can just simply write down this matrix multiplied by this column, so 2 and 3. And the answer is 2 times 2, 4, 3 times 12. So which is 16, I guess, and 6, 18, 24, and 32. Okay. So I get this column as a result, and I can translate this result as 16 times F1 and 24 times F2 and 32 times F3. Okay. So by just simply multiplying matrix by some column, then you can easily compute the result of this computation. Okay. All right. Now, well, these bases are like I guess these are easy bases, but there is no reason that we need to cling to these choice of bases. Maybe we can try to change the bases. Maybe one, 2 minus 1. And F1, F2, F3, 4, 3. So basis for the target space just remains the same, but I have changed the basis from E1 and E2 to these two vectors. Are they linearly independent? Yes, they must be linearly independent. And so I have two linearly independent vectors, so they can be a vector basis vectors for R2. Now, if I choose this basis, then let me try to write down the matrix representation of the same linear transformation, but this time around with respect to these two bases. Then T11 is, this is what? So T11, 6, 9, 12. Okay, so this is 6, 9, and 12. And what about the image of this vector? 2 times of first, 2 times of this minus. Oh, this is 0 vector, right? Okay. Now, do you think you can write down the matrix representation of the transformation using this basis? Yeah, I guess you can do this. I'm gonna say this is my basis B1. So in this time around, the matrix representation of the same linear transformation, but from now my input, the input basis has been changed from the standard basis to B1. And the matrix representation must be 6, 9, 12, and 0, 0, 0. Okay. This is very interesting. Yeah, even though I am representing the same linear transformation, but the changing the basis, my matrix representation also changes too. Okay. Okay. Now, what about, let me change basis just one more time. Now, this guy carries over. But I would say this is B2. Well, yeah, well, we are working on the exactly same linear transformation, but nothing changes but the basis. But this time, T of 1, 1. So in order to have the matrix representation of these bases, I must be able to write down these two resulting bases in terms of linear combinations of these basis vectors. Okay. 101 plus 100, 011 and 001. So what was this? So this was, well, this was 6, 9, 12. So 6, 9, 12. And this was the 0 vector. Oh, so I'm pretty sure that this guy equals to 0. They are all equals to 0. And now I wanted to find a linear combination that achieves this vector. So since this is 1, 0, 0, I guess this is 6. And this is 9. And 6, 9. And minus 3. I guess. Yeah. Okay. So the matrix representation of this linear transformation is 6, 9, -3, and 0, 0, 0. So this is a matrix representation with respect to these two bases. So, what do you learn from this? So, yes, the first thing is the matrix can be used to represent any linear transformation, as long as two basis systems are introduced for the domain space and the target space. But two seemingly different bases may represent, two seemingly different matrix of the same dimensions may represent the same linear transformation. Maybe not. So how do you know those two different matrices represent the same linear transformation or not? So this is very important question. So they're not that easy to find out. So this is very important topic, and maybe the most important topic in linear algebra. So how do we distinguish two different matrices represent the same transformation or not? So in order to find out, we will need to understand so-called the invariant of the matrix. So what is the invariant of matrix? Invariant of matrix can be computed just by looking at those numbers in the matrix. But so invariant plays a role like this. Suppose that you have computed invariant of each of these two matrices, but if those two invariant are different, then you're pretty sure that these two matrices are not representing the same linear transformation. So this is why we care about the invariant of the matrix. All right. So we will not be worrying about the invariant of the matrix. But however, this last proposition is somehow important, so I will try to introduce them. Well, this proposition is mainly about the composition of two linear transformations. Suppose I have two different linear transformations. The first one is coming from U to V, and second one, V, is from V to W. And the target space of F coincides with the domain space of G. And then, in this case, if you compose F with G, so G of F, so this is a linear transformation. Is it clear to you? Yeah. So maybe I don't need to prove the statement number one. So composition of two linear transformation is going to be another linear transformation from V to W. Okay. And statement number two is, this is interesting one. Suppose that I have chosen three basis system for each of these spaces. So B1 is for vector space U, B2 is vector space V, and B3 is for W. And since I have these three basis systems, and using all these bases, let me say this guy, A is a matrix representation of F with respect to from basis B1 and B2. And B is another matrix, so which represents the matrix or linear transformation G by using with respect to basis system from B2 and B3. Now, so in this case, so then what is the dimension of this guy? This is very important. So dimension of this guy is the row number of this guy must be the same as dimension of W, and the column number of this guy must be the same as dimension of U. And the row number of this guy is the same as dimension of W, and the column number of B must be the same as dimension of V. So multiplying B by A is possible. In terms of dimensions. Now, what I'm claiming here is this guy, this is the matrix, and this is a matrix representation of the linear transformation G transpose with F. with respect to basis B1 and B3. B1 and B3. So this matrix, this is B and this is A. This guy times this is a matrix representation of this one from B2, B1 to B3. So why is that? Okay. So let me say these are my basis vectors for U1 to UM. So the dimension of U is M, dimension of V is N, dimension of W is L. And let me say f of U, so f of Uj, this basis vector, can be written as a linear combination so from V1 to Vn. So these are my coefficient, right? So writing down these coefficients in vertical manner, so I can get a matrix representation of F with respect to basis B1 and B2, just like this. So just writing these numbers from top to bottom, you get this matrix, right? One by one. And same thing is true for basis vectors B. So G of Vi is also written as a linear combination of W's. And by doing so, I get a linear matrix representation of this linear transformation with respect to basis vector, basis B2 and B3. Okay. All right. Now, on the other hand, now I want to consider G composed with F. And I plugged in this basis vector to this composed linear transformation. But this is same as G of F of Uj. So F of Uj has been replaced by this, okay? But since G is also linear, so I can split this entire thing into these n terms, just like this. But G of Vi, but each of these guys from this one to this end, I want to replace each of these guys by this. So I get like this long tedious computation. But now I want to collect them in the like terms. So everything that has the W1 has been combined. So all these guys combined into the first parenthesis. Okay. This guy times this goes here, and this guy times this goes there, and and this guy times this goes here. Okay. And well, even though it is invisible, the same thing, I did the same thing for vector W2 and all the way to basis vector WL. So I will just compose all these guys and combine the like terms. Okay, good. Now what? Now, whenever just take a look at the first guy, the first guy is in this parenthesis, and J, well, what I have here. So the first index of A agrees to the second index of B. 2, all the way to n, right? Okay, so combining this, I can write down, summarize as a sigma notation from K1 to N. So I just changed the order because they are all real numbers, right? So B1K to AKJ. And K runs from 1 to N. And so this guy was written like this, and and this guy was written like this. So BL1, this index and that index, they are the same. They always agree. So I did it like this, okay? Okay, so what I did was I just plugged in this composed linear transformation, the basis vector, and the answer was written in the basis vector, another basis vector. So that means the matrix representation of this linear transformation in terms of basis vector B1 and B3, I have this matrix, and the jth column of this matrix must be just collection of these numbers written from top to bottom, right? Now, now let me just take a look of any random element, random component of this jth column. So if you take a look of the ith row of this jth column, which is ij component of this guy, is just like this. Okay, but this reminds me of the ij's component matrix definition of the matrix multiplication. This is precisely ij component of BA. So therefore, the proof has been claimed. So we just we just got to the conclusion of this proposition, and from this result, I will try to show how to change the basis of any given matrix representation. That will be introduced in my next lecture. Okay. Thank you for your patience, and see you next time.